Hey everyone, so today we're going to go through some really advanced back EMF concepts. So we recalled this formula from previously. Vnet is equal to Vsupply minus back EMF. This is something we should be comfortable with now. We can take this a step further by translating this into a new equation, which is the same thing but expressed in a different way. So we know that the net voltage becomes our net current, or just our current, times the resistance. Now, what is this the resistance of? It is the resistance of our armature windings, right? It is the resistance in our armature windings, right? So we can write this as R windings, is equal to our V supply minus our back EMF, okay? And then we're also going to change our V supply. So the V supply that we measure will be like, for example, here, right? And this the V supply that we measure will be across the battery. So that will be our V supply. Now, V supply will be very similar in size to V terminal. And V terminal is the voltage that you measure across the terminals of the motor. So a real life motor looks something like this, a bit like a cylinder, and then there's like a little kind of knob coming out, and then there are two terminals here, and you would hook up like a wire to this terminal. So the V supply and V terminal are very similar. We'll go through one small difference between them very soon. But just before we do that, this is our new equation. It is, as you can see, identical in the source to this equation. It's just expressed in a different way. Now let's quickly explain why V supply and V terminal are very related and mostly the same, although not theoretically purely identical. So if you think about if our voltage supply was 10 volts, then the voltage across our terminals should also pretty much be 10 volts. The only difference is if we consider that these wires have some voltage drop across them because there's some resistance in these wires. So we model this as a resistor. If this has some resistance, let's say it's 1 ohm, and then there's a current of 1 amp inside, then this wire would have a voltage drop of 1. And so with this one, so another 1 volt here. So that means that we would only see 8 volts over our terminal. That's unlikely because we tend to use short wires, and also because our wires tend to not be that resistive, but that's just a theoretical consideration moving between V supply and V terminal. Okay, so with this formula, we can now consider some more tricky concepts. The first of which is deriving a formula for the power, for the mechanical power output of our motor. Okay, so let's consider that the power total is going to equal to our power that goes into mechanical energy, mechanical kind of torque and making torque and stuff, plus the power that goes into resistive losses. So the total power, and let's also quickly record that P is a good IV, right? So the total power that we get in will be equal to our current. There's only one real current, times the V supply, but we can also write our V terminal, right? Both of these are the same, will equal to the mechanical power, right? So the mechanical power is something that we don't know, we want to create an equation for, plus our resistive losses, which would be again the current times our times the resistance of our windings squared. So there's also, if you recall, there's three formulas for power loss: I squared R and V squared of R. So then if we rearrange for mechanical power, oops, I can't do math. I think I'll do minus sign there. Then we want to do a little bit of a mathematical trick here. So we know that IR is equal to so we have an expression for IR from above over here, right? So it's equal to V terminal minus back EMF, V term minus back EMF times the current. And if you expand and simplify, what you'll find is that this whole expression will become I times so yeah, minus I times back EMF. I think I must have made a little bit of a algebra error somewhere here. Yes, sorry, this should be minus, so this is not minus. This is minus, sorry. And so we get P mechanical is equal to the current times the back EMF. Now let's quickly go through that derivation again. So we know that the total power is equal to the mechanical power plus the resistive loss. If we add together, we know that the total power is equal to our I times the voltage terminal plus is equal to the mechanical power plus I squared R. If we rearrange, we get P mechanical is equal to IV minus I squared R. We do a mathematical trick to isolate for IR. We know that IR from before is equal to the V supply minus the back EMF. And then if you expand this and simplify, you get P mechanical is equal to I times the back EMF. Now, I don't just want to give you an equation. I want to help you understand why this equation is true. So let's have a little bit of a think about why this is true. I want you to consider some cases with me, right? Let's consider some cases. So let's think about when the we will have this is speed, and this will be, so this is speed, and then this is sorry, time, back EMF, or speed actually. Speed and time would both be correct here. And we would see that it would kind of, back EMF would increase. So initially, our back EMF would be really small because our motor is not moving very much, right? And because it's not moving very much, our back EMF would be really small. But if we consider what our current, so let's also draw our current. Our current would look like this. This is our current. This is our back EMF. So our back EMF initially is really low and our current is initially very high. And that makes sense because the motor is stalling and it's not moving. So we have a lot of no back EMF, so there's a lot of current running through. So it's like that initially. So initially the mechanical power would be not super high. Over time, as current decreases but back EMF increases, we'd see the reverse. as we asymptote towards Vsupply, then our current becomes very small. So as we asymptote, then our current becomes incredibly small, and our back EMF becomes bigger. And it makes sense because in these two extremes, at a very high speed, after a very long time, and after a very short time, the motor is not doing very much work at all, because it's just spinning around, like at a high, over here, it's spinning around really quickly, but it's not actually doing much mechanical work because it's just spinning at a constant velocity. Similarly here, there's not much energy being expended, it's mostly being wasted as heat. Okay, I want to get onto some even more advanced topics now. These are getting quite advanced. So we want to answer the question of okay, so I want to answer the question of why can't you directly measure net voltage, Vnet. So if we quickly go up and grab that equation again, we're going to see that, so why can't we directly measure this? So, for example, if you were to have a coil here, right, and it's like rotating, right? If you have a multimeter, a voltmeter here, measuring the voltage here, right? And let's say that the voltage here is, 10 volts. And you might think, well, you know what, Bob, right? Like, because it's rotating, you have some Vsupply, then surely the voltage that I measure across the end should be less than 10 because there's back EMF being involved. But actually here we'd still measure 10 volts. Where it gets a little bit more interesting is if you were to measure something inside, right? So if you measure something inside here, if you were to stick a voltmeter inside the coil, so assume that this coil only has one coil, not more. It's an armature with only one coil, and you have a voltmeter inside here. And then we want to see what the voltmeter reading would have. Now, let's say that this might seem like a strange detail, but it's going to be pertinent later. Let's say that this distance here, this pink distance, and this distance combined is 25 meters, and this purple distance is 75 meters. That would mean that the reading on this voltmeter would be 7.5 volts. Why? So the first thing that I want to say is that the voltage that you're reading here, this is not the net voltage. In fact, this voltage you're seeing here is simply a function of the distance of this, of like how much, what percentage of the perimeter you're covering. Let me explain why that's true. So let's try to draw this again, but in a nicer way. And I must thank my friend Tammy Humphrey, she's a very intelligent woman, for helping me with this. She drew a wonderful diagram and inspired this. So what we have is let's get rid of this. So yeah. So as it's rotating, so first of all we need to consider that this coil consists of multiple smaller resistances, right? So you can imagine that there's a tiny resistance here, and a tiny resistance there, and a tiny resistance there, and each of these would be like some delta R, right? Some delta resistance, right? Another resistance there, and there's an infinite number of them, right? It would really be a dr, right? It'd be a very small amount of resistance. And then we're also going to have the back EMF being induced against us, right? We're going to have the back EMF being induced because it's a rotating armature, and this will be oppositional to our supply voltage. So the supply voltage creates a electric field in this direction, so the the back EMF must be in this direction. So we're going to have it'll kind of look a bit like this. So notice I have the long end of the battery to the long end here because it's opposing, right? So I'm going to have a few of these, right? And this will generate that should be a delta. Not that, sorry. So this would be some kind of delta epsilon, right? Something delta epsilon. Maybe I'll do it in red. Very good at this. Okay, and that continues around the entire side. Okay, so what that means is that if I was to grab, actually let me draw a few more. Almost there. Let me draw a few more resistors. Okay. So let's kind of have a think about this. So we're gonna have a voltmeter that kind of goes in between there, right? And when we have this voltmeter, what it's really doing is that it's kind of summing all the voltages across here, right? Summing all the voltages across here. So we can have a think about the voltages that would be across here. Now let's think about it in two cases, right? So this 7.5 volts that we found, not only is it going to be 7.5 volts if it's turning, it's also going to be 7.5 volts even if the machine is not turning. So let's cover that simpler case first of a non-rotational one, right? So let's consider it's not rotating, right? Not rotating. How do we get that 7.5? Well, this is the simpler case, right? So if it's not rotating, then we won't have this delta E, right? So therefore we can say that the voltage is equal to this, why would there be any voltages? It'd be the sum of these, little voltages, right? And the little voltages arise from these DRs, right? So we know that V is equal to IR. So if there's going to be a current running through this guy, then there's going to be some kind of voltage arising out of it. So it's going to be the sum of our I times our DRs, right? Of our delta Rs. And if we limit this, limit as delta R approaches 0, becomes an integral of I dr becomes IR, right? So the voltage is V is equal to IR. Now it's not just any IR, right? So this is not the total resistance of the whole thing, right? It's not the total resistance. If the total resistance is equal to like 10 ohms, right? Or like, let's choose a different number. Let's choose it's 6 ohms, right? Then this is the resistance of the resistors that we've summed along this pink path, right? So it would only be, it would depend on how long the path length is. If this is exactly like, let's say it's 60% of the total perimeter, then this would be like a sixth of 6, which is like 3.6. Pretty cool, right? So that kind of makes sense. So that's in a stationary case. This is not too profound. in a rotating case is more interesting. So let's consider a rotating case. So in the rotating case, our voltage, we're going to use a little bit of Kirchhoff's voltage law, but really it's not that extravagant. Our voltage will equal to the sum of our delta V's, right? From this is of the resistors, and also we're going to sum the delta epsilons, right? So again, as before, we have basically our IR times of the R of the proportion plus our the sum of the epsilons, and it's only going to be the epsilons across there, right? Plus epsilon, but plus back EMF. So again, if you kind of if you have if this pink path is 60%, right? If your total back EMF is equal to, like, 8 volts, then you'd only get 4 volts here, right? So this would be I times 3.6 from before, plus 8 onto 8 times 0.6, because you only get that 60% of that total 8 volts, because you only have 60% of the total path length here. Now, let's have a think about this. Why does it always equal to 7.5? So I asserted that it always equals to 7.5. And the reason for that is because as this thing begins to rotate faster, right? As it begins to rotate faster, that's how you get the increase in back EMF, right? But as back EMF increases, then your Vnet decreases, so your current decreases. So that's why that decreases. So you actually get a constant 7.5 volts. And finally, this brings us to the question of why can't we measure Vnet directly? Why can't we just measure Vnet across here? Why do we always measure V terminal and V supply? And the reason for that is because of this, right? So this term here is our Vnet, right? Remember that Vnet is equal to I current times the I times the winding resistance. So the problem is that as we, if we could somehow delete the resistance of the wires, right? If we could magically snap our fingers and delete the resistance of the wires, then this voltmeter would indeed show, this guy plus this guy plus this guy plus this guy, right? It would show the sum of all these delta epsilons. It would show you that, oh, the back EMF is 8 volts, right? It would show you the 8 volts. But the problem is, that you that in this process you can't just get rid of these resistors. You have to add them in, right? And so what you end up getting is you get all of the back EMF, all the red ones, so the 8 volts, and you also get 2 volts from adding all these little resistors together, right? And that's going to give you your 2 volts. There's no way that we can just delete all the resistors. And that's why you can't measure Vnet directly. You only can measure V supply. Thank you.